Wonderful. All right. So hopefully everybody's doing okay. Hopefully everybody is safe and healthy. And we are going to get into, usually we just do some practice here. However, we have a more challenging lecture and we didn't know if we were going to be back or not. It does seem that we are going to be back next week, which is awesome. So we are going to give you this lecture because we had already planned on it. And then next week might be kind of light and we will be studying for your test that is going to be at the end of next Friday. So let's go ahead and take a look. All right, so looking at this, we are currently in this week right now. History of the Atoms notes number 3 is what you guys did on Monday. History of the Atoms notes number 4 is what you guys did yesterday. And today we're going to do History of the Atoms notes number 5. And then we have a lab set up for you guys tomorrow that you guys should watch. Now, half of you have seen it, or half of you have done it, I should say. But I still have a question on the quiz about it. So if you want to refresh the colors of the photons in your head, make sure that what you wrote down is correct. I'll ask you a color of one of the flames of one of the chemicals. So you want to make sure you're taking good observations tomorrow, or when you watch the lab. You can watch it whenever you want. It's already posted. So then we will be back starting on Monday. So cohort A, I got an email last night from Dr. Kellogg that said that we'll be back. So we're going to talk about orbitals and light. And then we're going to talk about the history of the atom quick study. We're going to do a review. We'll do part 2 of the flame test where you're going to be given an unknown. And then we will have our unit test on everything that we've learned here. So it's all the way back. Atomic structure. It's pretty much going to be just bigger than the quiz this week, because this week's quiz, we also put the 2 days from last week. So we put almost all the scientists on there. So the unit test on the 11th is probably just going to be a little bit bigger. You'll have to be able to tell me what an ion is and an isotope is and everything like that. But we do have a review sheet we'll give you out, or you already have in your packet on the 9th. So you guys can prepare for that test. Okay. Then while we're talking schedule, because might as well just know what the schedule's doing, the last week, cohort B, we were going to give a little bit of a semester exam. We want to give you some time to work on a review packet. We will more than likely let you use that review packet on your semester exam. Really, truly, the only reason you give a semester exam as an educator is just to make the students think about all the material one more time. Okay, so what I'm thinking is we don't really have anything for Friday. So what I might do is give you one more review day and push the exam. And again, it will be in Schoology. It will have to be multiple choice or matching or anything like that. So it's not going to be super crazy. We started looking at it. We haven't finalized it, but we will let you know obviously in advance. So you might be taking this on either Wednesday or Thursday. And then if you're in class on that Friday, you will do your flame test. And then if you're not in class, then that's because you're taking the test on the lab day, you would just have that day off. So this kind of week is up in the air. Like I said, we just might add another review day in there. But the main objective is to see if you guys can just refresh and review what is matter, what is a heterogeneous solution, things like that. So it's just all about review. So that's kind of where we are at as far as what's going on in kind of our world for the next 2.5 weeks to get to Christmas or winter break. Does anybody have any questions over what we just talked about here? I think I saw some more people come in, so I want to make sure I'm getting everybody. Oh, there you go. All right, nice to see you. All right, so now we're at 20. All right. Oh. All right. So if we don't have any questions, then please feel free. This can be like a class. I'm looking at a sea of pictures, but oh well. If you have any questions as we go along, this material is a little more confusing. So make sure that you ask if you have any questions. The number one thing, I only have 2 people in here that have not watched all of the lectures. There were History of the Atom 1 and 2. That was last week. Those are closed. If you didn't get to those, let me know, and we'll make a plan to reopen those. And then 3 and 4 were this Monday and Tuesday. So hopefully you've watched all 4. All 4 of those lectures are fair game for the quiz on Friday. There is a lab in the Thursday folder that, again, is the only thing you have to do tomorrow, or you can do it today. We are in week 15. And in the folder is called the Flame Test Lab. Again, I'd watch that. If you want to see another teacher I found online who also does the exact same elements that we do, just in a different order, if you want to see another look at them, I think my camera was like zooming in and out, kind of weird. So if you would like to watch them one more time, this is a quick video down here of her going over hers. We will do participation points today. They are in the folder that you well, I guess most of you probably just went to Google and wrote Baycam too. But Wednesday live class here, the participation points are right there ready to go. The only thing that I'm going to do is I just changed it to say, if you came to class, or then if you didn't come to class, you just have to meet with me. So you guys will all go ahead and put A if you want to do that whenever. So let's do that. And then let's talk about Friday's quiz. It's going to look very short. It's only 5 questions, and it is 31 points. And people are like, what? How are we going to get to that? And then again, it is open from 7:30, and I think I even opened it up at 7. From 7:30 until 1:30, that is the class or your school day. So you want to make sure you take it. Nothing has changed with that. So we have 5 questions. One question is going to be an atomic structure chart, like we're about to do right now. All of the scientists are on there in one big, like, what did they do? What was their model type thing? So you want to make sure you've watched all 4 lectures, because if you didn't, then you would be missing a scientist. So it's got a pretty big question on that. It asks how an atom emits light, which is from Monday's lecture and from Thursday's lab. So you're going to do that. And then it has orbital charts that we're going to do today. And then it has a question about the flame test. So you want to make sure you watch that lab on Thursday. So there's 1, 2, 3, 4, 5 things about the quiz, and there are 5 questions. So you can do the math on that. I've told you what each question will look like. So the biggest thing, though, that I want to point out is there is a time limit on the quiz on Friday. Okay, and we're talking about Friday's quiz. It's only 45 minutes. So if you think that you're going to just look everything up, okay, that's not going to really work for you. You're going to run out of time. So you want to make sure that you know the scientists, you kind of have some idea of what each of them have done, all that kind of good stuff. I'm not going to extend the time on this one because I think it's very fair. It's only 5 questions in 45 minutes. So if you run out of time, that's because you were not prepared. So make sure when you sit down to take that quiz, you are prepared to know the 5 things, do an atomic structure chart, know the scientist, know how atom emits light, do orbital charts, which we're doing today, and then have watched the flame test. So that is Friday's quiz. Perfect. So kind of just jumping off of what you guys did yesterday, it's a little joke I would have had when you guys came in and it says, electron, it's proton, where are you? And on Heisenberg's uncertainty principle, he says, ooh, that's a toughie. I can tell you where I probably am. How about that? Because you can't know where an electron is and where it is going at the same time per Heisenberg's uncertainty principle. So what I want to do first is this is weird that I can't see you. I want to give you a few minutes and maybe I'll double check attendance while that's happening. I want you to get out in your packet structure worksheet number 4. Okay. You will have a chart like this on Friday. We thought about not putting it on there, but it's just been almost 2 weeks since I've seen you guys and had you guys do a chart. And this will be a big part of the unit test. So we wanted to make sure you still could do this on the quiz. So go ahead, and you also need a periodic table in order to do that. Periodic table. If you want to have a calculator, that works too. So why don't we have you go through, do a few of these. If you need a little refresher here, remember the atomic number, and you probably have this written at the top of your periodic table, which is fine. The atomic number is the number of protons. The mass number is the protons and neutrons. Remember, they're the only 2 things that have mass. And then the hardest one people usually find is the charge. You have to look at the 2 things that have charge. Protons are positive and electrons are negative. So because I can't see you and see if you have any questions, I guess I'll just pause for a few seconds while you guys work on doing this. If you have any questions or if you want me to go over anything, please let me know. And then you are going to do the questions at the bottom. Is an electron a particle or a wave? What does the Heisenberg's uncertainty principle say? And what is an orbital? So that's the last thing that you should have looked at in your notes from yesterday. So I'm going to double check attendance while you guys go ahead and fill this out. Please, 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 if you have any questions, don't hesitate to ask so that I can help you. The jam's on quietly here, I guess. Just like regular class, I guess. Okay, so that should have given you all a chance to go ahead and do some of this here. So let's turn this music off. All right, so we just did some attendance, and now we're going to go through and make sure that everybody understands how to do this. So the atomic number is the number of protons. If you don't have that information and you have the element, you just look it off of the periodic table. And so the number you should have gotten for this one was 28, and that's 28 protons. 59 minus 28 gave me 31 neutrons. And then the charge, again, is sometimes the hardest part for some people. Plus 28 minus 26 leaves me with a +2 charge. 14 tells me that that is silicone. And then I see I have 60 neutrons and I have 14 protons. So I know the mass is 30. And if I want a -4 charge, that means I need 4 extra negative electrons. So what is 4 more than 14? Would be 18. So minus 18 plus 14 leaves me with a -4 charge. I have 4 extra negatives, if you will. Iron, I look up as 26. That's how many protons he has. 29 plus 26 gives me a mass of 55. If I have plus 26 minus 23, that means I have extra pluses by the number of +3. We kind of started this one down here. 16 tells me that it's sulfur. If I want a -2 charge, 16 and 18 negatives would get me to the -2 charge. Bromine, I look up as 35. If the mass is 80, I do 35 minus 80, gives me a mass of 45. And then if I want a -1 charge, that means I need 1 more negative electron. So if I have 35 pluses, that means I have to have 36 minuses. And the question is an electron a particle or a wave? And that was our interesting lecture from yesterday. It's much more fun in person. But and the answer to that is both. It's called the wave duality of nature. And it also can be correct with light. Light can act like a particle and a wave at the same time, which is weird because it's like a particle and a wave at the same time. So Heisenberg's uncertainty principle says it's impossible to know the location and the movement of an electron at the same time. He was working off of Schrodinger's work that said that you really can't know where an electron absolutely is. And so he said you can kind of get a gist of where it's kind of going or where it is, but not at the same time. So they kind of got rid of the idea of these little orbits like planets around the sun, and they moved into this idea of orbitals. And orbitals are regions of space where there is a high probability of finding an electron. You are not guaranteed the electron in there, but it's just the high probability of finding an electron. And each can hold 0, 1, or 2 electrons. Okay? So that was our little bow work into here, making sure everybody was feeling good. So what we're going to do next is we're going to get into the history of the atom here. And then I want, okay, that one. All right, so the first thing I want to do is we were going to go in the notes. Excuse me for that. I'm very sorry that that was not ready. In the notes here, we're talking about how Bohr was mostly correct. What he didn't know that they weren't these little predictable paths. Like we said that electrons, he said electrons kind of orbit in this predictable path. You can tell me where it is, where it's going, and it's always going to come back to its same spot, kind of like planets around the sun. So I know that these notes are a little... They're my the version of my regular notes. I would, if you were in class, I would have you writing them in your notebook, but it's really impossible to draw some of these bubble charts. So we just decided to give you kind of these guided notes. So again, not trying to make it seem too easy for you here, but we're going to do these guided notes. So hopefully it's a little bit more clear because we are virtual. So what Bohr didn't figure out is that each of his orbits were kind of broken to different and smaller regions. Okay, so they weren't these little paths. And I think when they were naming them orbitals, they paid a little bit of homage to him in the idea that he thought they were orbits, and they're not, but they're orbitals. And remember, an orbital definition from yesterday's lecture is just a space that holds 0, 1, or 2 electrons. However, Bohr was correct on two things. He was correct that it takes a lower amount of energy to stay closer to the nucleus and a higher amount of energy to reside further away from the nucleus. So he was absolutely right on that. And so kind of how an atom emits light, all that kind of good stuff with the low energy and they jump and they fall, that's all correct. Bohr was correct on all of that. He just didn't understand how the electron actually moved around the nucleus. Okay, perfect. So what we have are these idea of orbitals. Okay, there are 4 different varieties. Let's break them down one at a time. The first variety is called an S shape. Okay, and the S shape only has one subset in it, and this is an S-shaped orbital right here. And so sometimes some people, for the shape of it, call it like a sphere, or you just draw a circle. And so you would probably say this is where you think, remember, this red part here is an orbital. Where these tines kind of meet, it would be the nucleus. And so what you see is that an electron, 0, 1, or 2 electrons are probably found in this, and this is an S shape. How did they start to figure out some of these things? Well, I have a 20-second clip here. Where did that go? Technology. Can't with it, can't without it.
Everything in the known universe is composed of atoms, but you should all
I don't even know if you can hear this like this.
The atom and the 3 fundamental
all right, understanding the atoms. So what I want to do, here we go. So this is kind of a little explanation that I think is good on how they figured out shapes like this. They basically took a bunch of snapshots of where, and it wasn't like a picture, but mathematically they figured out kind of where the electron was, and they put it together and they made what are these called orbitals.
Second, for a day, a week, and a manner with fixed energy around the nucleus, and then imagine that we take a picture of this electron every second for a day, a week, or month. We see that all these pictures laid on top of one another begin to form an electron cloud around the nucleus. Remember, all these hypothetical pictures or data points represent where the electron has been over time. If we now attempt to create a 3-dimensional surface to encompass 90% of all these data points, we obtain a sphere, which is often called the boundary surface.
All right. So what they have is they got some data points and they figured out where the electron was most likely around the nucleus, and then that's how they came up with these shapes or these orbitals. So there were data points and they said more likely this is where the electron has a high probability of being. So this is called an S-shaped orbital. The next shaped orbital we have is a P-shaped orbital, and there are actually 3 varieties of the P shape. There's one that goes in and out on the axis towards you, so like the z-axis. There's one that goes up and down, and then there's one that goes left and right. I remember the p orbitals as they look like a pair. They come in always two little shapes together. So I remember S is sphere and P is pair. And there are 3 of them. Okay. And again, all this is saying is that at this cross section is the nucleus, and these are the regions of space around the nucleus where there is the highest probability of finding an electron. Okay. Perfect. Highest probability of finding an electron. The next shape is a D-shaped orbital. And the D-shaped orbital, they actually have 5 different varieties. And I call them D for daisy. They have like these little lobes around here. So there's 5 of them. You can kind of see them back here. So there are some that are on the axis, some that are off of the axis. And then there's just like this really weird one. Again, they just figured this out mathematically, that those are the yellow and the red have meaning, but they're not important to us. This is just where there is a high probability of finding an electron. Okay. So I'm not going to ask you like the shape or anything. I just want you to have seen the different shapes, and these are where you have a high probability of finding an electron around the nucleus. Then there is one more orbital or shape that they mathematically predicted, and that's called an F. There are 7 of them, and they are just like twice as busy as the D-shaped orbitals. So again, here are my P for pairs. There are 3 of them. Here are my D for daisies. There are 5 of them. And then these are actually insanely expensive for what they are. So we didn't buy the 7F orbitals a long time ago. So this is what they would look like. But again, down here, all you see is that this is just how they are mathematically calculating where the highest probability of finding an electron is. Okay. All right. Good stuff. So now that we know the different shapes, how many varieties are in each, we're going to go through and we're going to put this all together. So what, and you are working in what are called quantum mechanics right now. And this is our most current operating model of the atom. So quantum mechanics is what everybody is generally accepting as how the model of the atom is, until somebody, you know, comes through and has a scientific breakthrough and teaches us something else. So what they know about electron motion right now around the nucleus is that there are different energy levels. So what Bohr thought was an orbit, okay, is more of an energy level. So if I could look into the energy level closest to the nucleus, okay, the area close to the nucleus, we would call that energy level 1. And in energy level 1, there's only one type of orbital. And in the first orbital, the only type of orbital you have there is an S. And remember, that only came with one kind of species. So here we go. So if you could look closer to the nucleus, there would be an S-shaped orbital around it. So if we were to take a look, and I have this other little animation, and for some reason it's opening up in the same program, so that's fun. Boop. All right. So this would be energy level 1. The intersection of this would be where the blue and the red and the green cross would be the nucleus. So what I'm flying in is one orbital. That's where it's a high probability of finding 0, 1, or 2 electrons. Okay, awesome. So then in energy level 2, if you could see a little bit further out in energy level 2, there are S and P shapes. So you have one of these, and then you have each of these over that. And remember, there's one type of S and 3 type of P. So S and 3P. So if you could see what that looked like, in energy level 2, there's another S shape. And then there's a high probability of 0, 1, or 2 electrons there, 0, 1, or 2 electrons there, 0, 1, or 2 electrons there. Okay. Then in energy level 3, you're going to see a pattern here. There is an S shape, a P shape, and the D shapes. S has 1, P has 3, D has 5. So the total number of orbitals are in energy level 3. So again, we're just saying in the next energy level out, energy level 3 would have all of those. So let's go here. So we have 3 starts with an S. Get in here. Get in here. Why are you not? All right. So 3S, P, and then, well, that's 4S, and then the D shapes would fly in there as well. So as you can see, it gets kind of cloudy in here. There's a lot of stuff going on. And then energy level 4, there's an S, P, D, and then that's when you add the F shape. So it gets really busy when we're talking about energy level 4. 1, 3, 5, and 7 here. You can have 16 different orbitals all around there. And if I kept flying those in, it would get way too big and way too confusing. Okay. So let's talk on each energy level, how many electrons can possibly fit, because you might have heard of this before. In energy level 1, if each orbital can hold 0, 1, or with a maximum of 2 electrons, 2 times 1, in the first energy level closest to the nucleus, you can only ever have 2 electrons. In the second energy level, each one, if it holds 2, you can have 8 electrons. In the third energy level, you can have 9 times 2 is 18 electrons. And in the fourth energy level, you can have 32 electrons. So you can see as it goes out, there's more room for the electrons to be because there are more of these orbital shapes. And again, it starts to get very confusing because they all overlap and all of that kind of good stuff. So we need a new model. So what they said, this new model and the model that we're working with now are called orbital charts. And this is an orbital chart right here. You can see the little bubbles, just like, and you want to look here, we have 1, 2, 3, 4 energy levels. You can see they're 1, 2, 3, 4 energy levels. It has the different, one just has an S, level 2 has S and P, SPD, SPDF, so all that kind of good stuff. So it's all kind of written here. The nucleus is down at the bottom, closest to the energy level 1. And these bubbles, each circle here represents an orbital. And what you do when you fill in this model is if you put a slash in, that is an electron. Okay, so now there are 2 scientists that developed rules in order to have fill this model in correctly. The first person is called the Aufbau principle, and obviously his last name was Aufbau. The Aufbau principle. And so when you're putting electrons in here, and he kind of went with what Bohr was saying, electrons fill from the lowest energy level first. So when you're putting your slashes, and this will all make sense in a second, when you put your slashes in here, you just simply start near the nucleus. So you need to start in 1s. You have to fill 1 before you can fill 2. You have to fill 2 before you can fill 3, except, there's always an exception. This is also known as ground state, right? Because Bohr said they want to be in the lowest energy, which is great, except for 4s. So if you take a look here, we have 1, which is S, then 2, which has S and P, and 3, which has S, P, and then here's the third energy level, D. But before we can put electrons in the third energy level of D, the fourth energy level of S sneaks in. And it's kind of weird. But if you can think about it algebraically, okay, and a circle shape, and you can kind of see if I line them up here like this, the electrons would be closer to the nucleus in a sphere than in these loby kind of daisy things here. So it's kind of hard to understand, but because in the D shape, they go way far out, it is actually less energy to fill 4s before you fill 3d. And if that's confusing, just go along with the little model here and you don't have to worry about it any more than that. The last rule is Hund's rule. And that's because electrons are negative and they don't want to be near each other unless they have to be. So you only put 1 electron in each orbital before you double up. So what you would do, for instance, let's pick an element like carbon. Carbon has 6 electrons. So what you do is you just go ahead and you put 6 electrons starting at the bottom. You would say we have 1, 2, 3, 4, 5, 6. And Hund's rule makes sure that you spread these out before you go back and force them into the same one. Okay, so let me do some more practice with you here. So let's do neon. If you can find your periodic table, neon here has 10 electrons. Its atomic number is 10. When he is a 0 charge, he has 10 electrons. So take your pencil right now, and we're going to put 10 slashes. Aufbau says that we're going to start at the bottom. Okay, and then Hund's rule says we can only put 1 in at a time before we double up. So with your pencil, you go 1, 2, 3, 4. Now spread them out. 5, 6, 7, 8, 9, and 10. Okay, so that is what is called the orbital chart. Then they just have you write what's called an electron configuration, where you write down what you see. So you kind of write it with a big number, the little letter, and then a superscript for how many electrons you have in there. So write down here, if you follow along, the electron configuration is 1s, and I have 2 slashes for 2 electrons. Then in the second energy level, I have 2s, 2. And then in 2p, I have 6. Okay, so what are those numbers telling me? They're telling me what energy level I have electrons in, what shape I have them in, and how many electrons I have in each of those. So it's kind of giving you a visual representation of something like this. Okay, we'll do one more example. I realize I'm close to end of class time, but so I'm almost here. Let's do one more. Iron, if you look at it, iron, he has 26 electrons, 26. So iron here, we see we would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, after 3p, 19, 20, 21, 22, 23, 24, 25, spread them all out and then go back for 26. Okay, and then all you do, and then I'll let you guys go because I'm sure you have another class, is you do your electron configuration. You just write what you see. 1s has 2 slashes in it. 2s has 2 slashes in it. 2p has 6 slashes in it. 3s has 2 slashes in it. 3p has 6 slashes or electrons in it. Then you do 4s before you do 3d. Now let's check. 3d had 1, 2, 3, 4, 5, 6. So you count how many you actually have in here. So what you've written down is where the electrons are around the nucleus. Okay, so we're going to pick this up on Monday. And here's a practice chart for you here. If you want, I will put the key online, which you're really looking for. If you want, here's the answers, or I'll just put it up online. But so you're going to look it up, argon, you look up its atomic number, that's how many electrons, you put them in there, and then you write down what every energy level has, what shape it has, and how many electrons it has. You always do 4s before you do 3d. Okay, so I'll put that key in there. I think I only put the bell work key in there. So I'll put this key in there as well. There is one question on this, just on the quiz. Make sure you abide by the 2 rules. Make sure you start at the bottom, and make sure you don't double up if you don't have to. Okay, so they always want to be in the lowest energy, and they want to be alone if they can. Okay, so that's what I have here. We're going to pick up with orbitals again. Watch the lecture or the lab for Thursday, and then take the quiz on Friday. And I will see half of you live in class, and then the other half of you go ahead and dial in on Monday. You cohort B, I will see you the same way here for Monday, and then I'll see you in the next week, okay? Hang around if you have any questions. If you don't have any questions, if you came late, let me know. I think I see more people than I... If you weren't here for attendance, hang on.